Welcome to the class. In last class we have seen that there would be Brayton cycle which will be with certain attachments, and in last class we have seen that Brayton cycle with heat exchanger attachment, and then we found out that if heat exchanger effectiveness is 1, then how to find out the thermal efficiency. Then we saw that there is Brayton cycle with reheater, and if we have reheater based Brayton cycle, then how to find out W net, Q in, and then what is the optimum condition for the reheat pressure for which we can get W net maximum. So this we have seen. Basically heat exchanger is used for getting maximum efficiency, and reheater is used mainly for getting maximum work output. So in last class there was one point which we saw was to find out efficiency with heat exchanger. This is the formula for efficiency of heat exchanger. Then we saw for reheater, and then we found out that this is the W net formula for reheater. We also saw that T1 is equal to T2 is equal to root T. We have to just remember that what is T1. T1 is the pressure ratio for the compressor. So this was T1. T2, sorry, this is T. T1 is the pressure ratio for the high pressure turbine. T2 is the pressure ratio for low pressure turbine. And when T1 is equal to T2, that means we have a constraint which we can feel here. T1 is equal to T2 means T3 by T4 is equal to T5 by T6, but we already know that T3 is equal to T5, so we will have T4 is equal to T6. So this constraint practically would lead to T4 is equal to T6. So this is an important point which we have to remember. Now we will go ahead and see the Brayton cycle with intercooler. For intercooler, basic objective is that we have to reduce the work input. We know that W net, which is the net work output of the Brayton cycle, is equal to WT, which is turbine work, minus WC, which is compressor work. Reheater increases WT, and intercooler job is to reduce WC. So reduce the compressor work. This is the job of intercooler. Again we will draw schematic of the arrangement for intercooler with Brayton cycle with intercooler. So this is now low pressure compressor. Air comes in and then it goes into a intercooler. Then it goes to the high pressure compressor. From there it goes to the combustion chamber. From the combustion chamber air goes to the turbine, and then from turbine it goes to the exhaust. So this is the path of the air. We have low pressure compressor, high pressure compressor, and then we have combustion chamber and turbine. But there is a intercooler, and then this intercooler is going to reduce the temperature of the air which is going from low pressure compressor to the high pressure compressor, intercooler. And again process of intercooling is isobaric. So 1 to 2 we will target, we will name them. 2 to 3 intercooling, 3 to 4 high pressure compression, 4 to 5 combustion chamber, 5 to 6 turbine. So process 1 to 2 we have high, we have low pressure compression, low pressure compression, and obviously this is an isentropic compression. 2 to 3 is intercooling, and obviously this is isobaric process. 3 to 4 is high pressure compression. Then we have 4 to 5, this is heat addition in combustion chamber. Then we have 5 to 6, which is expansion in turbine, which is obviously isentropic expansion. 4 to 5 is again adiabatic heat addition. 6 to 1, in case of closed cycle power plant, it is a pre-cooling. Having done this, we will again, like last time, try to draw the TS and PV diagram for the intercooling based Brayton cycle. So we have 1 to 2 compression process, then 2 to 3 is isobaric heat rejection in 2 to 3, then 3 to 4 is again isentropic compression. 4 to 5 is heat addition at isobaric condition. 5 to 6 is expansion process in the turbine, and 6 to 1 is the process which is pre-cooling process for closed cycle gas turbine based power plant. Having said this, we can as well draw the PV diagram, where we will have 1 to 2 as isentropic compression, 2 to 3 is isobaric heat rejection, 3 to 4 is isentropic compression, 4 to 5 is isobaric heat addition, 5 to 6 is expansion in the isentropic expansion in the turbine, 6 to 1 is pre-cooler process for closed cycle gas turbine power plant. So this is TV, TS and PV diagram. Now again we can find out what is the work interaction. What is the WC here? Here there are two compressors. So WC is W low pressure compressor plus W high pressure compressor. So WC is equal to Cp into T2 minus T1 plus Cp into T4 minus T3. Then we have Wt is equal to Cp into T5 minus T6, and then we have Qin, which is Cp into T5 minus T4. So if we are said nothing about intercooler on constraints and optimization, then we can go ahead and do the calculation as what we can do here. But the job of intercooler, as I told, is to reduce the compression work. So we have to maximize the reduction. So for this optimization, again our objective is to increase the W net, and W net is equal to Wt minus Wc. So W net is equal to Cp T5 minus T6 minus Cp T2 minus T1 minus Cp T4 minus T3. So this we need to maximize. So again the question over here, as what we asked for reheater, that what is the intercooler pressure? What is the intercooler pressure. So what is P2 is equal to P3 is equal to what? And for the W net max. So this is the question we have to ask ourselves, and for this question we have to derive an expression and find out. So for that we will go ahead. So for this question of what would be the intercooler pressure to get the maximum W net, we have to follow the same procedure what we followed for the reheater. So W net is equal to Wt minus Wc. So W net is equal to Cp into T5 minus T6 minus Cp into T2 minus T1 minus Cp into T4 minus T3. Okay, so W net is equal to Cp, we can take common. So T5 minus T6 minus T2 plus T1 minus T4 plus T3. Again we will look upon the constraints what we had think of. So constraints for optimization. The constraints what we saw last time was, one is Cp and T1 are known. So constants. So next constraint is Rp is known, so it is constant, and next constraint is beta, which is Tmax upon Tmin, and in present case Tmax is T5 upon T1 is constant. So for these three constraints we will do the optimization. So here we will get W net is equal to Cp, we can take T1 common, then it becomes T5 by T1 minus T6 by T1 minus T2 by T1 plus 1 minus T4 by T1 plus T3 by T1. So T5 by T1 is beta. So W net is equal to Cp T1, and then this is beta. So minus T6 by T1. So we'll do same thing. T6 by T5 into T5 by T1. T5 by T1. T6 by T5 into T5 by T1. Okay. Plus minus T2 by T1 plus 1 minus T4 by T1. So we will write T4 by T3 into T3 by T1. Okay, and plus T3 upon T1. We will again consider one thing as an assumption that inlet to both the compressor is same. We will put a constraint which says that T1 is equal to T3, which says that inlet temperature to both compressors is same. So having said this, we can go ahead with the next constraint, and we can write down W net is equal to Cp T1 beta minus T6 by T5 into beta minus T2 by T1 plus 1 minus T4 by T3 into T3 by T1 is 1. So plus 1. So we have W net is equal to Cp T1 beta minus T6 by T5 into beta minus T2 by T1 minus T4 by T3 plus 2. Now we have to carry forward this expression for the further differentiation. So for the same thing again we need few things. So this expression we can take it as W net is equal to Cpt1 beta plus 2. This is beta plus 2 minus T6 by T5 into beta minus T2 by T1. This is T6 by T5 beta minus T2 by T1 minus T4 by T3 minus T4 by T3. So here again let us consider what we had considered earlier, that T2 by T1 is equal to T1, T4 by T3 is equal to T2 and T5 by T6 is equal to T. What we are actually saying is this: as per this diagram we are saying that here if we say, we are saying that this is T1, this is T2 and this is T. So what we are saying is P2 by P1, suppose it is our P1 is equal to T2 by T1 bracket raised to gamma upon gamma minus 1. So it means that our P1, it means that T1 is equal to our P1 bracket raised to gamma minus 1 upon gamma. Similarly, what we have is T2 is equal to Rp2 bracket raised to gamma minus 1 upon gamma, where we are saying that Rp2 is equal to if we go in this diagram, Rp2 is equal to P4 by P3. And then similarly we can say that T is equal to Rp bracket raised to gamma minus 1 upon gamma, where we say Rp is equal to P5 by P6. Okay, so again we can see what is Rp1 into Rp2. Rp1 is what we have said, it is P2 by P1, and what is Rp2? It is P4 by P3. But we can see here clearly that P2 is equal to P3, since process of intercooling is isobaric. So this is P2 is equal to P3. So this is P4 by P1, but P4 is equal to P5, P1 is equal to P6. So this is Rp. So what we have is Rp is equal to Rp1 into Rp2. So what we would have is T is equal to T1 into T2. So we can do the same thing here. W net is equal to Cp T1 beta plus 2 minus T6 by T5, what we said was 1 upon T into beta minus T2 by T1, T2 by T1 is T1 minus T4 by T3 is T2. So this we have W net is equal to Cp T1 into beta plus 2 minus 1 upon T beta. So we can replace it T2 by T upon T1, and then we can differentiate this expression with respect to T1 W net, and we can get equated to 0 such that we expect W net to be maximum. We will get a constraint of this. So here again we have 4 terms, but in those 4 terms we have this term as constant and we have this term also as constant. So we need to differentiate only for 2 terms. So differentiation of this term will give us minus 1 minus, this will give us plus T upon T1 square is equal to 0. This would tell us again T is equal to square root of T1, or rather what we get is T1 is equal to square root of T, but what we have is T1 into T2 is equal to T. So what we will have is T2 is also equal to square root of T. So this is how we have got a constraint or intercooler pressure. So if we go back and see what we have achieved, so we got again that T1 is equal to T2, but we said internally that these two temperatures are same. So we said this is T min. So this ratio is same, that means this temperature is also same. So what we got internally by this assumption is T4 is equal to T3. Sorry, T4 is equal to T2. T4 is equal to T2. We should also know one thing, that what is W low pressure compressor is Cp into T2 minus T1. What is W high pressure compressor is Cp into T4 minus T3, but T4 is equal to T2, so Cp into T2 minus T1. So W low pressure compressor is equal to W high pressure compressor. So if we want to maximize the W net, then we get a constraint that both the compressors should have same work input. Similarly, when we were working for turbines, we also should have got the same thing for reheater constraint, that if we want to use the reheater for W net maximum, then we had got that for the constant maximum condition in the turbine inlet, we have to have same outlet temperature for both the turbines. So both the turbines should give same work output. So W low pressure turbine is equal to W high pressure turbine for reheater arrangement, and similarly we have W low pressure compressor is equal to W high pressure compressor for intercooler arrangement. Having said this, we have next thing to discuss is what if we connect everything. So we should do same calculation and similar way we should perform if we mix everything. So we have now a heat exchanger, plus we have reheater plus intercooler. In this we will just draw schematic which we had already discussed, but we will write down some formulas over here. So we have first a low pressure compressor. So it will have air inlet. So it is low pressure compressor. Before the outlet of low pressure compressor, it will go to the intercooler. So this is intercooler. Then from intercooler it will go to the high pressure compressor. So this is high pressure compressor. From the high pressure compressor, air will go to the heat exchanger. So this is heat exchanger. Then it will go to the combustion chamber, and from the combustion chamber it will go to the low pressure turbine. This is low pressure turbine. From low pressure turbine, gas will go to the high pressure turbine. So this is high pressure turbine. So from that we will have an exhaust initially going into the heat exchanger, and from there it will go out. So this is heat exchanger. So before that, from low pressure turbine to high pressure turbine, we will have a reheater. So now we have intercooler, we have heat exchanger, we have reheater. So all the attachments are connected. So let one be the condition at the inlet to the low pressure compressor, 1. Then we will have outlet as 2. Then we will have inlet as 3. Then we will have outlet as 4. Then 5 at the entry to the combustion chamber. Exit of combustion chamber is 6. Entry to the reheater is 7. Exit of high pressure turbine, exit of the reheater is 8. Then exit of high pressure turbine is 9. And then we have 10 at the exit of the heat exchanger. So now we should write all the formulas what we were writing earlier. Our formulas are this way, which states that we have plus WC is equal to W low pressure compressor plus W high pressure compressor. So WC is equal to Cp into T2 minus T1 plus Cp into T4 minus T3. Condition of optimization, if it is said, then we could have put it. But in general, what would be the case if we have all the attachments that we are mentioning? Then we have WT. WT is again W low pressure turbine plus W high pressure turbine. So WT is equal to Cp into T7 minus T6 plus Cp into T9 minus T8. So W net is as usual, which is WT minus WC. But what is Q in? Here Q in is again in two places, one in combustion chamber and one in reheater. So combustion chamber is Cp into T6 minus T5 and reheater is Cp into T8 minus T7. So this is the arrangement for all the attachments, and this is the expression for Q in. So thermal efficiency is W net upon Q in. If asked to us or if required, we can also calculate WR, which is work ratio and work ratio is equal to W net upon WT. Okay, but before that let us plot TS and PV diagram for this attachment. So TS, process 1 to 2 is isentropic compression, then process 2 to 3 is isobaric heat rejection in intercooler, then process 3 to 4 is isentropic compression, then we have heat addition in intercooler 4 to 5, so this is 0.5, then 5 to 6 is constant pressure further heat addition in combustion chamber, so it is 6, then from 6 to 7 we have high pressure turbine, then from 7 to 8 we have reheater, then 8 to 9 we have low pressure turbine, and then we have initially 9 to 10 heat loss, and then 10 to 1. So here this is how our cycle will proceed. So you can practice for this. Parallelly you could also draw the PV diagram for this arrangement. So this is how we have seen that if we consider first calorically perfect gas, second air is only working medium as constraint, and then if we consider different attachments like heat exchanger, reheater and intercooler, what would be the work and heat interactions, how to find out all the corner conditions like conditions at all points, and then what are the optimization constraints and conditions, and what are the performance parameters like W net and efficiency and work ratio. So in next class we will see about what would happen if the cycle is not ideal, that there are components like turbine and compressor who have efficiencies which are not 100%. So let's meet in next class. Thank you.